you very much. So first, let me thank the organizers for having me here, inviting me here. It's one of the first live conference that I am also doing, not the first. Actually, we were together at another conference before. It's also a trip down memory lane for me. As you will see, it's a field, transport in quantum systems, on which I've been really actively working recently, but in a completely different context than molecular systems, namely cold atoms. And I won't tell, of course, anything about cold atoms, although from Hans-Peter, I guess you already got a presentation of this. But so getting back to the molecular aspect of things and organic conductors and so on as a very distinctive flavor, and I'm very happy to give this talk. So this talk will have two parts. One part, very brief, which I will tell about magnetism. And this is a plea for compounds. So if there is a chemist in the room, please hear the plea. And then a second part where I will mostly discuss transport aspects. So this part will have a certain historical connotation. And it's very nice because many of the players which are involved are actually in the room. So this is good, which means all difficult questions should be addressed to them. Okay. So I'm switching. This morning was 2D triangular lattices, essentially. So I'm bringing you back down one dimension. And I would like to discuss a little bit the physics of one and quasi-one. So materials made of many chain couple. And we heard already about the Bechgaard salts, and they will figure in prominent place in my talk. But essentially, why is this physics interesting? So to cut a long story short, I don't think for this audience I need to spend too much time on this, but in 1D, interactions lead to very peculiar physics, which is very different from Fermi liquid physics in high dimension, in 2 or 3 dimensions. And even the smallest interaction can lead to dramatic effect. If you queued for the food at lunch, you know that in 1D, if you have interactions with the people around you, you cannot behave individually. You have to behave collectively, and the queue has to move collectively. You cannot just pass the person who is in front of you. So any individual motion is transformed into a collective motion. And in more scientific terms, this goes by the name of physics of Tomonaga-Luttinger liquid, which I will briefly describe here. So essentially, instead of individual excitation, Landau quasi-particles, Bogolyubov excitations, and the likes, what you get is collective excitations. And these collective excitations, quite remarkably, are described by essentially 2 parameters. One is the velocity of the excitation. The other is a dimensionless parameter, which controls the decay of physical observables. So if you have charge and spin, for example, like in Hubbard models, you will have one charge sector, one spin sector. And here is an example of the spin-spin correlation that you would get in a 1D material. There is a universal decay, 1/x² of this correlation, but there is an oscillating part, which is the antiferromagnetic part, if you want, which decay as a non-universal exponent, Power law, with an exponent which is controlled by this Tomonaga-Luttinger parameter case, one for the spin sector, one for the charge sector. The spin sector is always 1 due to spin rotation symmetry, or the sector is gapped if you have, for example, attractive interactions. The charge sector depends on the strength of the interaction. So as a result, you get these very peculiar quasi-long range order ground states, which are extremely susceptible to any perturbation you put on the system. So, for example, a 1D system will turn immediately into a Mott insulator if you have a lattice which is commensurate with the filling, while in 2D and 3D, you know that you need a critical threshold of interaction, usually, unless the lattice is bipartite, to get the Mott insulator. But in 1D, the catastrophe happens immediately, and there are many other similar instabilities. The second thing is that in 1D, the excitations can fractionalize. We are used into having elementary excitations that cannot be made smaller. If I take out one electron out of a system, usually I take out one charge and a spin 1/2, and I cannot do less than that. That's the minimum I can do, but not in 1D. In 1D, let me show you on this cartoon here. If you remove one particle, which is made of a charge and a spin, and you let the system evolve, then the spin will flip according to antiferromagnetic exchange, the natural Heisenberg-like exchange. And then after a while, you see that in a part of the system, you will get a region where no charge is missing, but there are two spin up close by. So this excitation carries a spin 1/2, but doesn't carry a charge. And people gave it a name, it's a spin-on, and that's a fractional excitation. And in the same way, if the charge is moving, then after a while in the system, you will get a region where there is a charge missing, but the spin alignment down, up, down, up, down, up is perfectly respected. And this excitation is a collective excitation which carries charge, but doesn't carry spin. And it's called a holon. I think Phil Anderson coined the name, but the excitation was known a long time before that. And so you see that our electron or elementary excitation has decomposed into a spin-on and a holon, one carrying spin and no charge, the other carrying charge and no spin. And in 1D, this deconfinement can be done arbitrarily. There is nothing which retain the spin-on and the holon together. I let you do as an exercise to put other chains around here and check that between the holon and the spin-on, there is a string of spins which is turned the wrong way compared to the other chains. So if you are in more than one dimension, the spin-on and the holon will be bound by a string, an energy string, which will grow as they separate. So actually they will form a bound state, and this is what you call a lambda quasi-particle. So this deconfinement and fractionalization of excitation is very natural in 1D, but of course doesn't carry out easily when you climb in higher dimensions. The second thing is because of what I just said, that there is a string of overturned spins here. The excitation has a topological nature, which is relatively easy to characterize in 1D. And again, in 1D, topological excitations are the norm rather than the exception. So many features will carry naturally this topological excitation. So all this makes it a very exciting physics to analyze. And of course, you want to find systems in which you can analyze this type of physics. So there are many questions. Of course, I will just address very few of them. The first one, I get spin charge separation. There must be consequences for the magnetism, and there must be consequences for transport, which are very different from what I would get in higher dimensions. So this is essentially the two topics that I will try to very briefly touch for the first one, just as I said, to give you a zest, and I hope we can discuss it directly during the coffee breaks. And transport, which I will do more extensively because I thought it would interest more people in the audience, but which unfortunately is much more ancient. You will see that most of the experiments I will show you are about 20 years old. The theories have made progress, but the experimental situation has been frozen in amber, and we need a Jurassic Park expert to take it out of the amber and reconstitute the dinosaur. Hopefully with new experiments here. Of course, the second type of questions that I will practically not discuss, but I'll be happy to discuss it privately, is how do you go from 1D to more than 1D? And this is a very up-to-date question. There is something called a dimensional crossover, where a system goes between 1D to 3D. And this is a very challenging question because, as you guess, it's as difficult as solving the 2D or the 3D problem, which is definitely not. And finally, something which is a big challenge that I will try to discuss is the Hall effect. Why is it special? Well, because to get Hall effect, you need to be more than strictly 1D. You need couple chains. On the other hand, if you're quasi-1D, there is a lot of things you can simply understand from the 1D physics. And if you want more details, there is a couple of references that I've put here. I can recommend a very good book on the subject of 1D. But there are also a couple of reviews. One which is very extensive on the organic conductors. There is a whole issue of chemical reviews that have been put together by Patrick Bataille, and which is devoted to those, not only the 1D, but also the 2D and so on. And more recently, a little blurb that was written in the compte rendu de l'Académie des Sciences, sort of summarizing 1D physics in the 21st century. Okay, so let me start with magnetism and just discuss magnetic insulators. Why do I love magnetic insulators? I devoted a sizable fraction of my time to studying magnetic insulators. Of course, they are an interesting problem by themselves. They have a lot of phases, spin solid, spin liquids, nematic phase, and so on. So this is remarkable. But they also exist in many materials, dimensions, with many type of exchange and so on. But they have also another interest, which is that contrarily to metallic systems, which have extraordinarily complicated interactions. You know, it's a screen Coulomb interaction, which depends on the energy and blah, blah, blah. And therefore, Hubbard models and whatever, Kondo models and blah, blah, are caricature of the reality. When we deal with insulators, usually there is a high energy scale, which is the charge gap. And then the exchange are very well characterized, and in many systems, very few of them. So they can be directly measured either by neutrons or by other probes, which means you know very well your microscopic Hamiltonian. And then you're competitive with cold atoms, meaning you have an Hamiltonian, which you know perfectly well, which is not a caricature of reality, which means if you could solve this Hamiltonian, you can get an exact description of the experimentally relevant quantity, which means you can do what people in cold atom have solved so well. You can do quantum simulations. You have an experiment, which is the physical realization of a given microscopic Hamiltonian. And by reading the experimental quantity, you have the answer, you have the solution of your Hamiltonian, even if you're not able to solve it on a computer or analytically or whatever. So this is a second use of a magnetic insulator, which I like, which is that they can be used as quantum simulators, and you will find this point of view expressed in this paper, for example. Now, yep. Yes. So we'll come back to quantum simulation platform, but depending on the platform, for fermions, for example, the temperatures are typically TF/10, which by solid state physics standards vaporizes the sample, the experimentalist, and the whole lab. So, but there are other advantages that I will mention later, the control on the interaction and on the lattice. But that's the point. With magnetic insulators, you can have your cake and eat it, because you can be at millikelvin, okay, 50 millik temperatures. You have 10 to the 23 atoms, and you know the microscopic Hamiltonian very well. The only thing you cannot do is the control of the parameters at the individual bond level, or even sometime at the macroscopic level, except by applying pressure or strain, as we heard. Yeah, you can do things, but in first approximation, you need a very good chemist friend. And if you don't like your couplings, you need to find another friend. So this is okay. Let's get to it. I like the spirit this conference is going on. Let's continue like that. Yes. No. So let me give you example. let me give you. Okay. Can I take a rain check for 5 minutes, and then give you examples, and then you can tell me whether I'm cheating you or not, which I am, of course, but after the while, yeah, you can. Yeah. No, but let me show you examples, because when I say it like this, it sounds a little bit crazy. But think about it. A spin 1/2 is a hardcore boson. Now, spin down is no boson, spin up is a boson. An Heisenberg model is binding hopping Hamiltonian of bosons plus nearest neighbor interactions. Chemical potential is the magnetic field. So you can do something that no other person is able to do. You can go from an empty band to a field band in 1D, in 2D, in 3D. Think about the guys who have a gate voltage and try desperately to dope by 5% in 2D. With magnetic insulator, you can do it. So you can realize hardcore boson on various lattices with nearest neighbor interaction and reading the spin-spin correlation function, which neutron people know how to do, NMR people know how to do. Think about it. S plus S minus is C dagger. It's the green function. It does the equivalent of RPS. As Z is density, density. It's the equivalent of compressibility and related measurement. It sounds like the dream system in which you can practically do a lot of things, except you have to have the system which is synthesized, which has the hopping and the lattice structure. But in that sense, it's a better quantum simulator than your iPad because it can do things much more efficiently than the iPad if you are on a frustrated lattice and so on and so on. So this is in that sense that they are quantum simulators. Let me give examples. So for that, there is a condition. One needs magnets which have a small exchange coupling force. If you have 600 Kelvin J, forget about using the magnetic field to manipulate the thing. Forget all what I said. You will not touch the system. So you need magnets with small exchange coupling constant. And in the last 20 years, there has been a revolution, I think, in quantum magnetism because people came with a lot of these systems and then they could be manipulated with a lot of these systems. Think about a dimer, a stupid dimer. If you have a J of 600K, this is a singlet, end of the story, boring. If it's a J of 10K, you put a magnetic field and you can make the dimer change from singlet to triplet. So you can manipulate it. But to get this small exchange constant is not easy, but in organic systems, that should be more easy than elsewhere. So this is a plea, please generate as many systems with small coupling constant exchange that, and we saw some examples. Let me show you others. So possibility to manipulate with magnetic field. And there is a price to pay for the theorist. Is that what we usually do to solve these problems? We say, oh, there is such a large coupling constant, J is 1000 Kelvin. We do field theory, long wavelength theory, blah, blah, blah. Now, if J is 10 Kelvin and the experiment is done at 1 Kelvin, this is not enough. So we need much more sophisticated theoretical method to compare with experiment because we do not have the 3 orders of magnitude or the 2 orders of magnitude we have to make RG work, to make, you know, field theory work, asymptotic behavior work, and whatever. So I won't go into the detail of the methods, but there has been a considerable development, theoretical development in the same period of time in the last 20 years, combining field theory with numerical calculations. Think about it. Numerics is very good at short distance, short time. Field theory is very good at large distance, large time. If you can combine both in a reliable way, you're done. And this is what we managed to do for quantum magnets. And of course, we are now trying to extend it to other systems, but you need these theoretical methods to develop what I would call essentially exact solution. I know in 1D that there are better ansatz solutions, which are fantastic, but usually if you try to compute sophisticated correlation functions, you don't go very far with the better ansatz. So you need numerically and analytically essentially exact solution, and you get it by combining various techniques. So let me just flash a couple of examples because I realize that my short part is getting a long part, but okay, that's... So for example, you can use it to simulate Bose-Einstein condensation. And this is something we proposed a long time ago with my accomplice, Alexei Zvelik, my friend Alexei Zvelik. And I won't go into more details. This is something you can do with ladders or you can do with dimers. So think about a dimer and you put a magnetic field. Well, if you polarize the dimer, there is still a residual degree of freedom, which is the projection of the spin in the XY plane perpendicular to the magnetic field. And then this is like a phase. This is like the phase of a boson. And by measuring these systems, you can realize BEC and do quantum phase transition by controlling the number of bosons by applying a magnetic field. So when the dimer is in a singlet state, there is no boson. When the dimer is in the triplet states, then there is a boson. And this is something that opened the whole game of research. And there are reviews here. We wrote a review with Christian Ruegg and Oleg Chernyshov, and there is a review by Vivian Zaff and the Los Alamos group on related materials. And now people know materials in 3D, thallium copper chloride. In 1D, I will show you the system. There was something that was believed to exist in 2D, which was the hand purple. Now it's a little bit more complicated than that. But you can do things with which you would do with bosons on a system. You can disorder, for example. You can manage to introduce disorder and then study experimentally disordered bosons, Bose-Glass. So this is a sort of very interesting and exciting direction. Let me show you how one can use this system to quantitatively test the predictions of the Tomonaga-Luttinger liquid that I was mentioning. So here is the system. It's called HPIP or BPCB, depending to whom you talk. So it's an horrible organic material where copper carry a spin 1/2. The magnetic exchange is about 10 Kelvin here, is about 3 Kelvin along the rungs here. And this material is made of relatively isolated such ladders. The interladder coupling is about 50 millikelvin. So there is a huge range in which you can view the material as 1D. So you compute directly from the knowledge of the Hamiltonian. You know the exchange constant, you compute the Luttinger parameters. And from the Luttinger liquid theory, you compute the NMR relaxation time using the Luttinger parameters you have extracted from your Hamiltonian. And this is the measurements that were done by Martin Klenczek in the group of the late Claude Berthier in Grenoble. The circles are the data points, and the red curve is the theoretical curve without any adjustable parameter. So this is a quantitative agreement between theory and experiment, as it should be, because we know everything there is to be known in this system. The only unknown is the hyperfine coupling constant, which the experimentalist knows not too well, but not too badly. But in any case, this would just be a multiplicative factor on the whole curve, but would not affect the shape of the red curve, which is computed for all magnetic fields. Sorry, the horizontal axis is the magnetic field. The figure is cut here. This is about 7 Tesla. This is about 13 Tesla. And this is when the system has all the dimers are in singlet states, and here all the dimers are in triplet states. So this is where the Luttinger liquid exists in between these. So this is a remarkable, I think, case, because we can do something which is quantitative on this type of systems. Here is another system in the group of Andrei Zeludev in ETH Zurich, where they use another compound that I will show you in a moment, which is called DIMP, to extract from the neutron scattering experiment the S plus S minus correlation function, which is the single particle green function for the bosons. And you can again, so here is the neutron data. And the black curve is the Luttinger liquid scaling. You can put it into a scaling form, which again is perfectly well known in 1D, with an exponent here which depends on the Luttinger parameter, which again you know from the microscopic of your Hamiltonian. And therefore, you see the agreement between the scaling and the data point. The amplitude here is an adjustable parameter, but again, the shape of the curve is you can even play the Hamiltonian reconstruction just to show you how good we are now in solving this problem. Initially for DIMP, the exchange constant were not known. This is more or less the opposite of the previous ladder I showed you. This is about 3 Kelvin and this is about 10 Kelvin. In order to determine this exchange, what we did was to take various Hamiltonians with various exchange constants, compute the neutron spectra, and then compare with the neutron spectra at zero field until we found something which gives the experimental neutron spectrum. So here is what we get. The data is the experimental data points. The full curves are the computed neutron spectra. So here we are very happy. We get the excitations right. And this allowed us to extract the coupling constant that I gave you in the Hamiltonian. And then based on this, we can compute other quantities. So here is the Hamiltonian. We can compute other quantities, like, for example, this compound has a transition to an ordered state. And here, the red curve is the prediction based on this extracted coupling constant. And the dots are measurements of specific heat singularity. And you see again, it falls on the curve. There is one number, which is an adjustable parameter, which is the interladder coupling constant, but that's one number for the whole curve. It orders three-dimensionally. So this curve is, these curves depend on one parameter, which is the interladder coupling constant, which we adjusted. But you see that if we adjust it for 1 point, we fit all the other perfectly well without any problem. The ordered state is below the dome. So you put a magnetic field, the dimers polarize, but they still have this residual phase perpendicular to the magnetic field. And then below a certain temperature, all the projection in the XY plane align in one direction. So this is XY order and 3D. I think they didn't have a magnet which was going beyond 15 Tesla. So for this one, we don't have the data and they don't have the data. But as you see for the HPIP, there we are pretty good. Okay. Yes, yes. So this is a triplet that you have on the ladder. So the lowest triplet goes down, the other stays constant, and the last one goes up. So the small magnetic field is not equivalent to the largest magnetic field. The triplet and the singlet cross. So there you have a kind of symmetry because you can view the singlet and the lowest triplet as two components of a spin 1/2. But when you include the other excitations, it's not symmetric. And actually, I didn't comment on it. The green curve here is the restriction to the two lowest states. And then it's symmetric, but you see also that it doesn't explain the data. So the method is sensitive enough and the experiment is sensitive enough to measure this difference. And we, of course, use this mapping to check that we were able to do it. So this is just the degree of accuracy that this type of experiments can lead to. So now there are disordered versions of this HPIP. So one can study 1D disordered systems. Again, I won't go into the detail of all the things that we do. You can use the fact that there is another triplet, the triplet 0, which you can excite by neutrons. Then you have one triplet 0. All the other rungs are triplet plus or singlets. So this is like one hole in the TJ model. So you can do a kind of quantum simulators for looking at one hole in a TJ model. And again, we can play with this and analyze other quantities. Okay, so I'll stop. Here is a new compound that was synthesized in the group of Chris Landy. This is a ladder again, which has practically isotropic exchange. So 10 Kelvin and 12 Kelvin. So this is sort of bridging the gap between the strong rung and the weak rung ladders that I showed you. And again, this is the measurement of the susceptibility. The red curve is the numerical calculation that we can do, and you see it agrees very well. Again, this is a plea. We need more new molecular quantum spin systems, not just to multiply these examples, which we know how to do very well, but because then it would be fun to have frustrated lattice, triangular lattices, disordered system, system for which the interladder coupling or interchain coupling is stronger than in these compounds. I told you 50 milli-K for the HPIP, it's pretty low. So either one uses the system directly as a quantum simulator to get the answer, or it will help benchmarking more sophisticated numerical techniques, in particular when the coupling between 1D units is concerned, because this is the limit of what we don't know how to compute essentially. We do RPA, we do mean field, but it's not a very, very good method. Okay, I think I'll stop here for the magnetism. Before I go to transport, are there other questions on the magnetism? Yes, Antoine.
Can you establish the data on top of simulated data? You still have your gap.
Yes. 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 It's not worse than having a four-leg ladder, for example. So the question is not again so much, can we do more degrees of freedom? We can. We could do up to 6, I forgot, legs without too much problem. The question is more, is the Hamiltonian we're going to simulate a realistic description of the experimental compound or not? No, not at the moment. But at the moment, we have another horrible compound that I don't dare to talk about because it's mineral, it's not organic. It's called Bakovo. No, I'm joking, of course. It's called Bakovo, and you know, I would say God invented HPIP and the devil invented Bakovo. It has every complication in the book, but it's so beautiful. It has topological phase transition that are described by a double Sine-Gordon model. It shows Pokrovsky-Talapov transition. It has everything, and it has very complicated interchain couplings that we are trying to understand, because at the moment it's a complete mess. We don't understand. It's a spiral. Each chain is actually a spiral with periodicity 4, which is coupled to another spiral with periodicity 4. And that makes for very interesting interchain coupling, which can cancel when the magnetic order is commensurate. But as you polarize the system, this cancellation changes, and that makes for new phases. So it has a very interesting sequence of phase transition, something we are looking with people in Grenoble and Paris on neutron scattering, Virginie Simonet, Véronique Brouet, Béatrice Grenier, sorry, in my head, Béatrice Grenier and Sylvain Petit. And on the theory side with Shintaro Takayoshi, who is faculty in Japan and at some time was a postdoc in my group. And we are having a lot of fun with this compound, but it's complicated. Yes. 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 You can look at my name. No, I'm joking. So I'll give you the reference, but essentially the idea is a method that was, as many things in 1D, invented by Haldane, which is that you use the numerical possibility to do a calculation of the Luttinger parameters exactly from the numerics. In addition, you do the amplitudes of the correlation function that you can also extract from the numerics from the short distance behavior of the correlations, and that you inject in your field theory. And for short distance, short time, we can even, of course, get directly the correlation function from the DMRG, because DMRG up to times which are 20 times the microscopic time will give you the time-dependent correlation. So it depends at which energy we have to go. Either we do brute force calculation of the correlation from the MRG, and then we switch on for field theory for the NMR, for example, or things like this. Yeah. Are there other questions on this? Okay, if not, let's go to transport. So transport will be much less modern, although we'll see. And more importantly, I owe many, many thanks to many people. I could not put all the names, so please don't be offended if you're in the room and if your name is not on the list, but you will certainly recognize Martin. Actually, there are two authors of paper I think we did together, which are sitting side by side. And of course, the most important was my former PhD advisor, Hein Schulz. But there are many, many people. Antoine is also there. So we committed some physics prime together. Okay, so let me go to the Bechgaard salts because they are, to the best of my knowledge, I won't say the only, but certainly one of the unique realization of quasi-1D metallic systems. And again, the plea is we need more compound like those. So they were synthesized now 40 years ago by Klaus Bechgaard. This is molecules that you already saw, which are flat, which means that essentially, actually there is, depending on whether you get sulfur or selenium, something called either the Fabre salt or the Bechgaard salt, depending on people who did them. But essentially, the main point is that there are stacks of these molecules which have a very strong anisotropy in the electronic conduction, where electronic conduction is best in this direction, a little bit weaker in the perpendicular direction, and the weakest in the direction where the chains are separated by ions. This is a salt, so the charge transfer is complete, and we know exactly how many charges there is in the band, and this is a quarter fill band. Actually, it's a 3/4 fill band. It's a quarter filling of holes. And the hopping integral, if you want to do a tight binding, which again now becomes a caricature, is about 3,330 K, just to write simple numbers to give you the hierarchy of scales. They are quasi-1D, and therefore they have very interesting properties. I should add that they have also a small dimerization, which is greatly exaggerated on this image here. So actually, when I say the band is 3/4 fill, it's not true, because the dimerization is opening a gap, a band gap, far from the Fermi level, but as a result, the upper band is half filled. So these systems, because of the dimerization, are naturally Mott insulators. And because of this, the dimerization play an important role. And you see that it's supposed to go down a lot when you go from the TF salts to the SF salts. And so people said the change of behavior between the TF salts and the SF salts, these are essentially insulators, these are essentially metals, is due to the disappearance of the dimerization in the system. And of course, what made these compounds famous is the discovery in 81 by Denis Jérôme of superconductivity at about 1 Kelvin in this compound. Now, the question we could ask is, do we care? Because we know other materials which are regular, not organic, which are superconductors at a much higher temperature. So at the end of the day, do we need to worry about the Bechgaard? So my answer is yes, we do, because not because of superconductivity, maybe, although the nature and the mechanism is still not elucidated, but they represent an example of strongly correlated 1D physics. And you see here their conductivity as a resistivity as a function of temperature. They are clearly materials. We go from nice insulators to more metallic here behavior as you move along the family or as you apply pressure in this system. And here is their combined phase diagram. So you can put the various compounds here on this phase diagram, or you can take the most insulating of them and apply pressure, as was done by Didier Jacquard in Geneva. And you go from spin piles phase, antiferromagnetic, spin density wave. Okay, this line is a little bit for decoration here. And then superconducting phase here at a very low temperature of 1 point something Kelvin. Okay. Now, the question you might want to ask is, are these compounds Tomonaga-Luttinger liquids? At least above 300 Kelvin, let's say, when the hopping between the chains is not yet relevant. And there was a lot of debate on this at the beginning. And for example, you can look at the charge transport and the spin response, the spin susceptibility, and it varies a lot, while the spin response doesn't vary much. So some people say, haha, that's the proof of spin charge separation. So they are 1D Luttinger liquid. On the other end, the transport was showing a nice T-square law up to 300 Kelvin. So there are other people who said, well, T-square, I'm sorry, this is a Fermi liquid, and that's it. That's boring. Now, the T-square law got a little bit shot in the wing when people realized that theorists are computing at constant lattice spacing and experimentalists are measuring at constant pressure. And these compounds are like accordions. So when you warm them, the lattice spacing changes. So you should correct for this. And when you look at the dependence, it's more like T square below 100K and more like something like T at higher temperature. And therefore, it's not crazy now to imagine that you get a change of behavior at about 100K. And so the debate was there. And what clinched the debate is very beautiful experiment that were done by George Brunner, Leo De Giorgi, and Martin. So all questions should go to Martin, which is measurement of optical conductivity. Here is the optical conductivity as a function of the frequency in this material. And you see that in addition to the Drude weight, which is occupying here an insane place because of the logarithmic scale, but this is a ridiculously small frequency, you get a huge peak here, which is actually due to the MOT, or let's say the insulating nature of the material, even if there is a little part at low energy, which is metallic. And this peak has a very sort of characteristic shape. And when you compute the transport in a Luttinger liquid, you find that this is a little bit what you expect. You expect something which starts at the MOT gap and then goes down as a power law with an exponent which reflects this non-universal power laws and which is dependent not only on the Luttinger parameter, here it's K rho, but also on the order of commensurability. So if you have a half field compound, N is 1 in this thing. If you had a quarter field compound, then you have a higher order Umklapp term, which is scattering things from one side of the Fermi surface to the next, and N is equal to 2. So technically, measuring this tail gives you access to a kind of combination of a Luttinger parameter and the order of the commensurability of the filling of the band. And so if you try to do it with the experimental data, you see that all these compounds, depending on the independent on the ions, have essentially a same rescaled frequency behavior. And at the end, you get a pretty decent power law over more than 1 decade, which is, this is roughly the bandwidth of the system. So don't expect Luttinger liquid to hold to more than the bandwidth of the material. And this is one, here is the gap, so, or the energy scale corresponding to what would be the MOT gap in the absence of interchain coupling. And so don't expect, again, things to hold below this. But in between, it's a pretty decent power law. And when you try to extract the numbers, you find that half filling would not really cut it because it would give a K which is so close to 1 that it's incompatible with whatever value of the interaction you want to have in these materials. It would mean 0 interaction in these materials. And on the contrary, you have to say this is dominated by quarter filling, Umklapps, and the K is now pretty small, actually. It's, let's say, 1/4 roughly, which means not only strong interactions, but also more than on-site, means interaction which can extend to the next molecule. So transport gave the answer. No, dimerization doesn't seem to be super important, at least for this property, and the interactions are pretty strong. So yes, the normal phase here is actually a Tomonaga-Luttinger liquid, and this is reflected in the transport property. Now, of course, the question is down to where can we expect the Tomonaga-Luttinger liquid? And for that, we have to worry about the fact that there are coupled chains. And of course, the interaction effect vary a lot with the dimensions. So we have to worry about this interchain coupling, which is about 300K, as I said. I forget the third direction, which is much smaller. And there, it's well known that you will get a dimensional crossover when the temperature is large compared to this coupling. Particle hop incoherently from one chain to the next. So you see the 1D behavior. And if the temperature is smaller than this coupling, then essentially you're coherent. So you have a 2D or a 3D material. Actually, in 1D, this is a little bit more complicated. The interaction renormalized the energy scale down because the electron has fractionalized. In order to hop, it has to recombine and hop, which is difficult. So when interactions are non-zero, this scale is not T-perp, but is renormalized by interaction. And lo and behold, when you do this, you find that there is a scale which is compatible with 150 if you inject the value of K that was extracted from the other transport. If the lower phase is gapped, then you get a more complex phase diagram where you get the energy scale for the gap, which would go down. Then you get a sort of deconfinement of the 1D excitation. This is by increasing the interchain coupling here. And then you have a metallic phase which appears with a coherent scale, which is supposed to go up, of course, as you increase the kinetic energy compared to the point at which you get, let's say, something not well defined here, but which should be a quantum phase transition. Okay, so in order to probe this, you can look at transverse transport. And transverse transport is interesting because the three-dimensional coupling is very weak. So actually, if you do transport along the C direction, what you do is you do a tunneling experiment because it's always incoherent unless you go below 10 Kelvin. So what you're measuring is the single particle density of state in the planes. So if the chains are decoupled, there are no single particle excitations. Resistivity will go up with the temperature. If the chains are coupled, there is single particle excitation, and then the resistivity will go down. So you expect in the resistivity along C a peak at the dimensional crossover temperature. And lo and behold, these measurements were done in the team of Denis Jérôme by Joël Moser. And you see very clearly that there are some peak which appears in the C-axis resistivity. And of course, you want to identify the scale with the dimensional crossover. Very much more precise and sophisticated experiments were done by Martin Dressel later, where you see very clearly that the resistivity along the chains and perpendicular to the chain do not follow at all the same temperature dependence. And by using this result, one could extract the fact, okay, let me skip this. One could extract the fact that there is indeed, when you apply pressure, which is a complicated thing because pressure will do many things. It will compress the materials, so increase the kinetic energy along the chains, but it will also probably bring the chains closer together. So it increases the bandwidth, which means it diminishing the interactions, but it's also increasing T-perp. But definitely, if you measure the gap scale that you see from chain transport, it goes down. Then you see this crossover scale going up, and you want to use this as an evidence that there is this deconfinement transition that is happening around. Okay, let me skip this maybe because otherwise it will be way too long. These are the conclusions from transport, both longitudinal, optical, and transverse, that you have this, and at the end that the dimerization is not super important, and therefore that the change of behavior from TF to SF materials is more likely due to the fact that you change the interactions. You make them a little bit weaker, and then you pass through the quantum critical point at which the quantifilling umklapp is not relevant. So this is a supposition, if you want, but borne by the transport results. And that you would have a dimensional crossover at an energy scale of about 100 K. But this leaves several puzzles, and these puzzles were never solved because there is only the goddamn compound, and we don't have very much comparison. Actually, it's not completely true. For the dimerization, there was another compound that was synthesized by the group of Patrick Bataille, where they removed the dimerization. So this is a stack of chain, just like the Bechgaard salts, but because of the way they assemble the material, this system has absolutely no dimerization along the chain. And it still has this is inverse temperature, and it still has a resistivity, which is going up as the inverse temperature goes up. Which means it's an insulator, which proves that you can get a quarter field Mott insulator in this material. What is interesting is that this material, so its properties have been investigated by, again, transport. And when you look at the phase diagram and the pressure of this material, it seems to have phases. So it's metallic, then it's again an insulating phase, which disappears. But so far, to the best of my knowledge, nobody has found superconductivity in this material. Is it just because for this material, the superconductivity is at too small a scale, 1.2 Kelvin for the Bechgaard salt? If it's half a Kelvin, then probably something else can destroy it. Or whether there is an intrinsic reason why this material should not be superconductor. The ball is in the air, and one would need other systems to be able to experimentally answer this question. Of course, theoretically, we are not able to go down here because we need to solve the problem of many coupled chains, and that we don't know how to do. There is another puzzle from the NMR, is that the 1/T1, actually it's a very old puzzle. 1/T1 is very anomalous at low temperature in the Bechgaard salts. And initially, because of this, this temperature was interpreted as the one of the dimensional crossover. But now we know it's wrong. We know it's not the dimensional crossover. So this anomalous behavior is in the 2D and to some extent 3D phase. And so one has to come with a convincing mechanism that would lead to this type of behavior in the now coupled chain phase. And so far, nobody has done that. So this is a phase that still need to be described, and out of which the superconductivity, of course, will emerge. The question of coupled 1D chain is a mess, so I won't discuss it. We tried to attack it by many directions. We don't want, we tried to do what would be now known as cluster DMFT. I expect at the time we call it chain DMFT. So we take one chain and treat the rest of the chains as a bath. And with the help of Christophe Berthaud, Silke Biermann, and other collaborators like Sasha Lichtenstein, we tried to address this problem. But of course, it doesn't, so I won't discuss this. We could get some interesting effects, but nothing that would explain certainly the superconductivity. More recently, I just want to mention this recent paper together with Adrien Cantillon. We tried another approach, which is to do it more brute force by coupling chains in a DMRG procedure and trying to extrapolate as the number of chain is growing quantities. So here we were extrapolating the spin gap, for example, and found that there is a spin gap that seems to survive as we couple chains. But of course, this is an extremely difficult calculation. The ball is clearly still in the air. Okay, let me, well, I guess I just have 5 minutes or something like this. 5 minutes, okay. So let me just flash the Hall effect. Because I think I don't need to tell much about the Hall effect. The Hall effect, you all know what it is. Everybody is lying to you, telling it's measuring 1/n. That's not true. It's more complicated. Otherwise, TLLS would have never gotten the Nobel Prize for the topological formula giving you the Hall effect. But all this is for non-interacting systems. And as soon as you put interaction, the Hall effect is an open question. And it's a very complicated problem. We had an attack again with Antoine a couple of years ago, but let me skip that and just show you the more recent calculation we did with former PhD student Gladys Léon and Christophe Berthaud. Here is what theoretically we think is happening, is that you get a deviation from the classical value of the Hall effect with a power law that reflects again the Luttinger liquid nature of the system. Okay, so what do the experiments say? Well, here is the result from the team of Denis Jérôme, which sees something which is relatively compatible with what I was telling you, deviation, which you could fit as a power law. Okay, here they fitted it as a power law starting from 0, but you see a strong variation in temperature of the Hall effect down to the place where you get the dimensional crossover. And then it tends to go back to the classical value. Then you get order, and that changes. But there is another experiment which was done in the group of Laszlo Foro at EPFL on the same compound, slightly different measurement in the other direction, but it should not matter above the dimensional crossover temperature. And this time they see an essentially flat response of the Hall effect. Who is right? Who is wrong? That's an experimental question which needs an experimental answer. To the best of my knowledge, down 22 years later, this question is not resolved. They swear that they took every possible precaution. So this is a question you should ask both Denis and Laszlo, but yes, they swear it's the linear part of the Hall effect and in magnetic field and the current, and that they cancel the misalignment of the contact. You know, who am I? I'm just a theorist. I have to believe what the experimentalists tell me. At least one of them is wrong. Or maybe they are both right because they did two different geometries. We think that this should not matter, but maybe it does in a way we don't understand. So I'm just throwing this at you to, these are 4 probes. So, no, this is not Corbin. No, this is the, you know, needles. Okay. Yeah. The 2D is about, if you believe the transport is about here. Yeah, 100. Here you don't see much happening. You see something a little bit lower at 100K. It's the 510 to the minus 3, and on the other side, this is 10 to the minus 9 meter cube. So, okay, I won't dare doing the conversion on the top of my head right now, but they are in different directions, huh? So they don't have the same hopping integrals in the. Okay, so I'll stop here on the Hall effect. I'm throwing you this, and I think that will be the end of my talk. Just to whet your appetite and say you shouldn't give points to people in other fields. I just announced that tomorrow there will be a paper, or tomorrow maybe beginning of next week, there will be a paper with the experimental team of Lens in Florence, where we studied the Hall effect in cold atom systems. And these people are able to measure it for a ladder by varying the interactions and compare with theoretical predictions. Again, they have the control on the interaction, which is remarkable. What they lose is the Fermi, the temperature is 1/10 of the Fermi temperature. So it would be interesting again to have both sides of the story together. Okay, let me conclude. I try to convince you that we have this incredible flexibility and richness of coupled one-dimensional chains. We have now firm evidence of Luttinger liquid physics, both in the metallic and the insulating compounds. There is evidence of a deconfinement transition. And at low temperature, there is a phase, which is a Fermi liquid phase, that still remembers that it came from strong correlations. And there are many, many open questions, but I think the main is that we need other components and we need other probes to tackle these things. Everything that could be measured on the Bechgaard salt has been measured, except maybe the Hall effect. So there are a certain number of questions, and perhaps at the end we'll understand superconductivity. And on that, I stop, and I thank you for your attention.